Welcome all. So today we will start the fourth part of the kinetic theory of gases as well as the thermodynamics. That is basically here. First, I will just give the difference between the classical and the statistical thermodynamics. What is classical thermodynamics? Means that is the relationship between the bulk properties of matter. Nothing is examined at the atomic or molecular level, so it is a bulk level. So actually when we are considering at the bulk level, we are basically missing a lots of informations that is related with this the thermodynamical phenomena. So that's why we are just considering the statistical thermodynamics, where we can consider in the microscopical approach. So microscopical approach means we are considering the constitute of the materials are constitute of atoms, and the statistical part treats the aggregation of atoms, not the behavior of any individual atom. So it is a kinds of this the lots of the fact or the data points we will get, then only we can get the right assumption. So that is actually the using the statistical phenomena is very important, and that's when the Maxwell-Boltzmann statistics we are basically following for these thermodynamics systems. So what is the first law of thermodynamics? The first law of thermodynamics you people are already know from your plus 2 level. That is the change in the internal energy of a system. The change in internal energy of the system is equal to the equal to the heat flow into the system. Okay. So plus work done by the system. So here you can see, just here it is just showing with the an image, that is the ideal gas. We are just putting the ideal gas, and the piston is basically movable inside. When it will move inside, then we are considering it is this what I discussed in the quasi-static process, that it will goes not very fast, so sufficiently slow process if we consider, then infinitesimally the slower we can that means infinitesimally equilibrium process we can consider there. So that's why we can say the del U is equal to Q plus W. That means here the Q, what is Q signifies? Q is the internal energy of the system, and W is the work done by the system or on the system, and del U is the basically the change in the energy, okay, or the heat flow of the system. So an isothermal process is one where the temperature does not change. Now here we know that when we draw the Boyle's law, that means P and V, P varies 1 by V. So the nature of the curve is basically like this, that A or B or A prime and B prime. So when higher temperature is there, then we are getting this curve, and when the nature of the curve is the same, only the the position is basically changing. Okay. So the first law of thermodynamics is an extension of the law of conservation of energy, actually, because the change in internal energy of the system is added here, and the internal energy of a system is equal to the heat added to the system minus the work done. That means the total internal energy is equal to the amount of heat imparted on the thermodynamical system minus the work done by the system. So Q minus W. So in vice versa we can write also Q is equal to del U plus W, right? So it depends upon that the when it will be worked on, that is we will discuss it later. So the displacement work, that is the PdV PdV. Why it is PdV? If the volume will change, then we are saying it is PdV. Why? The dW is basically the pressure, the force and the displacement, right? So the force, first is the force exerted is the pressure into area. So here we are just put, instead of F we can put P into A into dl. So ultimately the dV, so the P into dV is the expression of the dW, mathematical expression of dW, right? So now if we want to find out that what is the work done by the system or on the system, then we can just do it simple integration, that is dW is equal to the integration of PdV. So the dW means what? The dW is basically the meaning the work done by the system or on the system. Here you can see that PdV, so the pressure is constant, only the volume is changing. So that's why we can get this work done. Okay, so now the thermodynamic process. What is the thermodynamic process? There is a 4 process we are considering. One is isobaric. Baric means bar is the pressure and iso means similar, same. So when the P is constant, then it is called the isobaric. Next is the isochoric. So isochoric means when the volume is constant. Similarly isothermal means the temperature is constant. And lastly is the adiabatic, when PV to the power gamma is constant. Now I am telling you the isobaric, isochoric and isothermal, it is a basically for the ideal gas systems we are basically implementing these 3 part PVT, but when we are considering the real gas, then the adiabatic process is basically implementing there. So the PV to the power gamma is equal to constant. What is gamma? I will discuss it later. Okay. Now the adiabatic process. What is the adiabatic process? Because now we are coming with a new terminology, that is adiabatic. So the adiabatic is basically where the no heat exchange across boundaries of the system. So what I told you, the quasi-static process means where the heat is basically exchange at the boundary, right? So if that means from thermodynamical system to the surroundings, if the heat will exchange through the boundary, then it is isothermal process. That means the temperature of the system is not increasing, right? But in the adiabatic there will be no heat exchange. So that means it is totally insulated. And generally for real gas it is happening when I am just giving you the instant example that when we are doing the cycle pumper systems, when we are using the cycle pumper systems, we are not doing it in a very slow process. We are just pushing the piston very fast, and if you just noticed, the pistons will be heated very fast. And how we can just reduce the heat of the systems? By that we are just making it some stainless steel or the metal. Basically the metal, thermodynamic system is a metal system, so it will radiate the heat. So that's why, but it is really very heated, so that's why it is generally adiabatic process, because we are here considering the real gases, so it is not ideal gases. So that is the main difference, fundamental difference between ideal gases. In ideal gases we are considering quasi-static process. So in the adiabatic process, so no heat exchange will occur, and adiabatic process transfers no heat, right? Next, therefore Q is equal to 0, so del U is equal to Q minus W. In the adiabatic process it will be Q minus W, right? So next, when a system expands adiabatically, then W is positive. The system does work, so del U is negative. So then del U is negative. So when a system compresses adiabatically, W is negative, work done is the system, so del U is positive. So now you can understand that if it is a expands adiabatically, there is a 2 systems I am just explaining here. When we are considering the adiabatic process, that means the related with the this real gases, then what is happening, that W is positive, the system does work. So at that time system is basically working, and when the system compresses adiabatically, means W is negative. That means work is done on the system. So work is done on the system. In case of refrigeration, it is compresses adiabatically. When we fast compresses adiabatically, that's why in the compressor, if you we better to not touch. I mean, it is just given this caution that you should not touch the compressor systems of the which is in the back portions of the refrigerator. So because it is very heated. Why? Because there is a compression of the gases, and when these compressions will occur, then it will be heated, and when the expansions will occur, that is in the radiating system, radiator, in the radiator the gases will be suddenly release the pressure. So what is happening? That is work done on the system. So when the work done on the system, then what is happening? That it will be cooling very fast. So that is it is basically, sorry, when the system does work, the del U is basically negative. So that means at that time the refrigeration, that means cooling is occurring. So when it is expands adiabatically, then it is cooling, and when it is compressed adiabatically, then it is heating. Okay, work done is done on the system. Now what is isothermal process? Again, isothermal process is a constant temperature process, so it is a quasi-static process, we can say, and it is very slow. We are just considering it is very slow, and how much it is slow? It is basically slow enough to maintain the thermal equilibrium. So it will maintain the thermal equilibrium of the system. Okay, so next, what is the next one? That is actually the isothermal process. That is for ideal gas, if del T is 0, then del U is equal to 0. So therefore Q is equal to W. Any energy entering the system, Q must leave as work. So here what is happening, that in isothermal process, actually the internal, the Q, the amount of heat is equal to work done. Okay, so here because the internal energy is 0 as the T is 0. Okay, and any energy entering the system must leave as work. Okay, now next is the isobaric process. In the isobaric process is a constant pressure process. That means del U, W, Q are generally non-zero, but calculating the work done by an ideal gas is straightforward. How it is? That W is equal to PdV. So water boiling, like in saucepan, if we will do this, in saucepan there is no lid, so is an example of isobaric process, because the water, it will not create any kinds of pressure inside the systems. Why? Because the lid is not there, so it will easily communicate with the surroundings. So whatever the heat is generating, and the pressure is basically generating by the heat. So just you think about the pressure cooker system. In the pressure cooker system, what is happening? Just use your common sense, that during in the hill area where the water is very fast, the boiling, there we are using the pressure cooker for getting the boiling of the substance, because the water is boiling very fast. So there what we are doing in this case, that we are using the pressure cooker, where the due to the pressure, first the temperature will the temperature will increase in the system, and when the temperature will increase, it is increased very rapidly, so it will not communicate in the surroundings. So then that means the temperature of the systems will increase, and if the temperature will increase, then the thermal agitation of the gas molecules, corresponding gas molecules, that is also increase. So when it will increase, then it will create the pressure or thrust on the wall of the systems, so automatically the pressure will increase. So if the pressure will increase, then cumulatively the temperature, the boiling temperature will decrease. So this way we can increase, we can do the boiling of the object. That means, like suppose I want to boil the potato in the hill area, then you have to use the pressure cooker, right? So this is the examples of the systems which is not isobaric. So when the isobaric system means like there is no lid, so that means the temperature, the pressure and the temperature will slowly in the equilibrium state. Okay, so now here you can see the P versus V. So when the P versus V, there is the A and B, the two state of the systems, we are the thermodynamical systems we are saying here. So when it will just approach from A to B, then the pressure is same. So then it is called the isobaric process. That is the graphical representations of the systems. Now we are going to isochoric process. What is isochoric process? An isochoric process is a constant volume process when the volume of a system does not change. It will do no work on its surroundings. So W is equal to 0. That means the volume is here 0. Del V is equal to 0. So del Q is equal to, then del U is equal to Q, because the PdV, you know that dV is the work done. PdV is equal to work done. So here if it is a work done is, I mean the system, that means the work done is due to the dV is not changing, that means isochoric process. So there is no work done on its surroundings. So then W is equal to 0 and del Q is equal to Q. Del U is equal to Q. That means internal energy is equal to amount of heat. So heating gas in a closed container is an isochoric process. So heating gas means what? That means in the if we will just heat the gases in a closed container, then it will an isochoric process, just like this one. That means it will just go from A to B. So here the pressure is changing, but the volume is the same. So this is the examples of isochoric process. Okay. Next, the first law, if we'll just combine these three, that is isochoric, isobaric and isothermal, then what we have seen that the straight line, there is a straight line for PA to PB. If we'll go, then here the volume is not changing, so it is a isochoric process. When D to B, then the isobaric process, that means the pressure is not changing, only the volume is changing. Whereas B to A, the volume and pressure both are changing simultaneously. I mean both are changing means simultaneously. Why I am saying these things? Because if one is increasing, then another will decreasing in nature. Sorry. So what is happening here? That the isothermal, this is the isothermal because the temperature is nearly the same. That means whatever the temperature is generating there, this is actually radiating to the surroundings. That is called the isothermal process. So in one graph we can just represent the three part, right? So the sign conventions of the first law of thermodynamics, that when the heat flow into that Q, capital Q is the quantity, that is the heat flow into the system. So when the heat flow into the system, then the heat flows into the system meaning positive sign, and if it is negative sign means heat flows out of the system. So if it is positive sign, that means heat flows into the system, and when it flows out of the system, that means it is negative sign. Similarly, work done on the system, that is, if it is positive sign, that means surroundings do the positive work on the system, and if it is negative sign, that is basically the system does positive work on the surroundings, just reverse, or we can say negative work on the system. So that is the meaning of the W. Similarly, del U is the internal energy change, and when it is positive sign means the internal energy increases, and if it is negative sign, that means internal energy decreases. So that is the meaning of positive and negative sign. I think this is a very good way of remember yourself that what is the meaning of the by the system and on the system. So simple thermodynamic process of the first law, that is isothermal when T is constant, that means Q is equal to, it is a summarized part that which we discussed so far. Here you can see here that the predicts like this way, that here you can see the del U is equal to 0, so Q is equal to W. Isobaric means P is equal to constant, that means here the Q is equal to del U plus P dV P del V. So P is constant, that is not a problem, but here the pressure is constant, so there is no problem with the del V. Whereas the isovolumetric, at that time, that is the isovolumetric means the isochoric process, when where the volume is the constant. So del V is equal to 0, so ultimately W is equal to 0, so Q is equal to del U. So next is the adiabatic process, that is Q is equal to the amount of heat is equal to 0, that means the del U is equal to minus W. Okay, so that we just summarized the what we discussed so far, and then in other words we can say that a rearrangement of the previous slide, that is the W tends to 0 and W greater than 0, for the system doing work on the environment, and another is the for the environment doing work on the system. So that I already discussed. One is the system is working on the environment, another is the environment is working on the system, right? So that is the amount of energy. So our focus is the energy in the ideal gas system doing work on the environmental removes energy from our system, right? So what is the applications of the first law, that is the kinetic theory and internal energy? So predicting the specific heats of dry air, I already told regarding this that the why I'm just first started with the kinetic theory of gases, and after that I am coming to the thermodynamics. So here you can see that the quantity of the heat absorbed per unit mass, that is the material, when temperature increases 1 Kelvin or 1 degree centigrade, then it is called the heat capacity. So two types of heat capacity are basically present in case of gas molecules, because one is the specific heat at constant volume, another is specific heat at constant pressure. So this CV and CP. So what is the CV means? CV is basically the heat capacity at constant volume, that means when it is related to 3/2 into R, it is a constant, right? And the R is the gas constant, that is 8.314 joule per Kelvin per mole, that is already I discussed. So this is the why it is this 3/2 R, that is already you did in the plus 2 level, so I am not going in detail about the derivation on that. So for constant volume, what we can write, that Q, the constant volume Q is equal to N into C del V into del T, so it is del U, right? So the universal gas constant, you know, that is the values of 8.314 joule, I told you already, right? So this is the expression, and here we are considering PV to the power gamma is equal to constant. You can remember that I mentioned the adiabatic conditions. So gamma is the ratio between Cp and Cv. Okay, so the value of gamma is equal to 1.4. okay, so you can write this on your notebook because it is not mentioned in this slide. Now what is reversible and what is irreversible process? This is very important to discuss, the reversible and irreversible process. So actually, example, we can say that an ice cube placed on a countertop in a warm room will melt. The reverse process cannot occur. So suppose reverse process means if we withdraw the heat, then whether we can get it? Yes, but this is not happening spontaneously. So that's why it is not a reversible process. Okay, a collision between two billiard balls is reversible because the momentum is conserved here. So this is the examples of reversible systems, that when the momentum of the two billiard balls are happening, they collide to each other, then the momentum is conserved if time is run forward. The momentum is still conserved if time runs backwards. So that is because it is an elastic collisions, that's why we are saying this, the two billiard balls collision is a reversible process. Okay. So any process that involves dissipation of energy is not reversible. That is the clue points what I want to mention here, that if any process that involves dissipation of energy is not reversible. So any process that involves heat transfer from a hotter object to a colder object is not a reversible. So when we actually got the whatever the energy we lost. If we'll gain the energy in the when we are coming back from one point to the another, means where we go when we lose this energy, that if we will retrieve this energy, retrieve this energy, then only it is called the reversible process. Okay, so this is the examples of the two already I discussed here. So now we will just conclude here, and in the fifth part we will discuss the next one.